Hello and welcome back, and we're finishing off. We're in the second video for elastic and inelastic collisions here. So I just want to talk about what is the difference between the two and try to give you kind of a visual representation of what's going on. So you can see I've already drawn the carts down the left side, and those are going to be our visual aids here in seeing what's going on or understanding what's going on. So in the first stage here, instead of graphs, what we have is I have two carts screaming at each other at some high velocity. It's not really that fast, and the one has a spring on the front of it. So it's essentially acting like an ideal bumper here. So in that case, the force, F of x, okay, or spring force, is 0 in this case. For obvious reasons, there's nothing acting on it. So in that case, just going to have a dot right here. It's fully extended, so that's what that is there. That's the extension. Its natural rest position. Okay, so that value, I guess I'll transfer it. Let's call it value A, just so you know that's why it's there. And it's the same thing on the other graph then, about the same distance. Okay, so it's still in fully extended position, hasn't been compressed yet. So in both cases, regardless elastic or inelastic spring, that's what's happening. So we start to get some compression in stage 2. So now there has been contact, the spring has begun to compress, but it's not completely compressed. All right, so there is some compression. If this was an elastic situation, then what will happen in an elastic situation is that there's our starting point, compression begins, so there is some spring force contained. So it begins to look like that, and it's the exact same for an inelastic situation, an inelastic spring situation. So they are identical at this point. Now the third one, what we're going to do is we're going to go full compression. So what does that mean? It means that the motion is paused. Okay, they've come to a full stop because the spring is now fully compressed. It's as far as it's going to go. And when you look at the resulting graph here, that means that that delta x is all the way back. So here's the starting. It's now a full compression, so delta x is equal to 0. Okay, it's as far as it's going to go back. And again, that's true for both graphs. So try to draw the identical line there. So there we are. So nothing inelastic springs or elastic springs, it's going to be the same situation. It's the fourth one where, I guess you call the magic happens. So we now have the spring force shoots the carts off in separate directions, and that spring is allowed to return to its original length. If we have a pure elastic situation, then it returns to this location. Okay, so maybe what I'll do is I'm going to put a dashed line or a dotted line in, saying that it's gone back to its original rest position. All right. In the inelastic scenario, okay, so something was lost. So inelastic's more of a real world scenario here. It returns back here. The difference is, if I use that dashed line, this is what elastic looked like. The path that it actually follows, and I'll just draw it in green, it's going to return like that, a nonlinear relationship. And in that area, the area difference here, so this area in here, this represents lost energy. So that could be the sound of the collision. It could be the heat that the spring, or the transfer to heat energy from the spring being compressed. So that region there under the curve between where it theoretically should have done and what it really does or actually does is that energy loss. So what you're going to find as you go through your university level math courses and some of the college courses, area under the curve is a lot of times that's the focus, is we want to find that area under the curve. So that region represents the energy loss. So in the elastic situation, or sorry, inelastic situation, that's why we're concerned with it, because it's not ideal. In an ideal world, this is what happens with a pure elastic collision. But inelastic, energy is not conserved, only momentum. Okay? So trying to give you a visual aid as to what is happening or what are we really looking at here. Now I have a flow chart that I've used from other years. What I'm going to do is I'm going to go through and I'm going to fill it out So it's going to appear filled out in a minute, and then I'll talk about it for 1 second. And so you might want to, when it pops up, pause it before I go through and do the discussion. All right, so the chart's filled in. So for some people, this chart's going to be a hindrance more than anything, because you're going to know from either understanding concepts or just from the practice, you get a feel for what you're supposed to do. What this is supposed to help out is some of the people that are unsure of what pathway or what choices to make. So we've talked about this. Collisions occur. There are 2 of them. They can either occur in 1 dimension or 2 dimension. So if it's in 2D, then we're going to be using our vectors to deal with 2-dimensional, can't spell vectors apparently, but we're going to use vectors in order to work with the 2D situations. So let's go down to 1-dimensional. So this is a head-on collision. So i.e. head-on collision. All right, just to give you an idea of what we're talking about in 1D. So in 1 dimensions, we're talking about head-on collisions. So there are 2 types of head-on collisions that we can deal with. There can be elastic, all right, or there can be inelastic. So you need to A, find that or locate that in the question as to which it is, or B, infer which situation we're dealing with. And it's not like it's going to be some big dark secret. You're going to be able to figure it out as to which one it is, because it's going to be reflected on the homework example and the examples done. So let's say we determine it to be elastic. For elastic, we have 2 situations. If the velocity of the second object is 0, so the impact, it's an object moving and it strikes another object that was stationary at that point in time, then we can go down that first pathway. So we can just go ahead and say, okay, the second object wasn't moving at the start, so we can use the V prime and the V2 prime formulas that we generated in that proof earlier in this note. No other work is required. If that velocity is not 0, then we got to come across and go into the next column, which is the same as an inelastic situation. Or sorry, it's not the same. There's no connection here. All right, that's the dead end for an inelastic. So just be careful with that. If V2 is not equal to 0, then what happens is that we need to change the frame of reference. And I'm going to do an example. You're going to see an example of this. So if you're not sure as to what that means, I will do an example. Then you use the formulas that we generated from our proof. Then you'll return to the original frame of reference. That's going to be forthcoming. So this is kind of a chicken and egg situation. I haven't done an example to show that, but it's just showing you the pathway. If we decide the 1D example is inelastic, so this would be, and in the question I would put, they 2 cars meet and result in a huge fiery wreck, and it's just chaos and carnage everywhere. That's inelastic, all right, if there's damage. Elastic, it might be 2 pool balls strike each other, or 2 physics carts with their physics bumpers hit each other. So those are perfectly elastic. Inelastic's a little bit more with the real world. Your only option then is to calculate momentum. You cannot use any of the formulas other than the momentum equation. The reverse, the 2D, so if the cars are not coming head on, so they strike at an angle to each other, you still have your 2 decisions. If it's a fiery wreck and no one knows how the survivors walked away from it, it's inelastic. Your only option is to do momentum. If it's elastic, if we're talking about pool and the cue ball strikes the 8 ball, okay, you can use energy, all right? You can use momentum. The only thing you need to remember in order to use 1/2 mv squared is that the formulas only work for components. So you'll have to take the x component of the velocity, the y component. All right, energy, remember, it's a scalar value. It doesn't have magnitude, or doesn't have a direction. Momentum, a little bit nicer because it is a vector, so you can do your IJ format when we add and subtract vectors. So just keep that in mind. All right, some of you are not even going to look at this chart again, and some of us will return to it to help decide how to deal with a particular word problem or situation. So let's take a look at a couple of examples here. So a 5 kilogram bullet, or 5.5 gram bullet, fired at a suspended 2 kilogram block of wood. So this is what we call the bullet pendulum. So it looks like this. So here's my block of wood, And here's my approaching bullet at a very high velocity. After impact, the wood swings back such that the height changes 13 centimeters. So in green, I'll redraw it. So my block of wood rises up 13 centimeters, which is 0.13 meters. Okay, and now that bullet is embedded inside the wood, so it's gone up. What was the velocity of the bullet just before it hit and became embedded in the block of wood? So you got to ask yourself, what type of collision is this? Was there any deformation? Was there any carnage? The bullet entering the wood, there'd be splinters. It would be mangled, the bullet. So therefore, inelastic collision. All right, this is definitely an inelastic collision. So this is where it gets kind of dicey when I go through and do the explanation. So according to this, if it's inelastic, my only options then, it's a 1D situation, I got to use momentum. So when I come back to this question, I want to use momentum. So what I'm going to do is I'll work up here. So momentum. For momentum, I know M1 V1 plus M2 V2 is going to equal, the bullet sticks inside, and I guess it would be VT to show the after. We're going to use this momentum equation. So when I go and fill in the information, 0.0055 for the mass of the bullet. I don't know the velocity of the bullet. That's what I'm looking for. Now mass 2 is the mass of the block. It's 2 kilograms. It's not moving, so it's 0. Mass total is 2.0055. And I don't know the velocity that the block is moving backwards. I don't know VT. So that means I have two unknowns in this particular equation. So VT, and this one goes to 0. So that must mean I know some other piece of information. And this is where people start crying foul. I'm going to figure out the velocity of that block using energy. Okay? So I'm going to do this in green over here using energy. And I'm going to take a second to explain this, because now you're saying, wait a minute, you just said for inelastic collisions you can't use energy. Yes, because we know EK does not equal EK prime. What we're going to do is we're going to analyze either, so it's a one or the other, either the before or after collision. All right. Oops, collision. Okay, so before the bullet hits the pendulum, okay, so if we have this situation, EK1 will equal EK2. All right, oops, not a vector, sorry, because no collision has occurred. All right, or the bullet in the inside the block, afterwards, EK3 would equal EK4. However, EK1, which is equal to EK2, is not equal to the after situation. All right, so you can analyze prior to the collision or you can analyze after the collision. You just can't take those energies across the border. You can't do it saying before is equal to the after. So that's why people, when they see me using energy, all of a sudden they're like, oh, wait a minute, this doesn't make any sense. But remember, you can analyze the before or after. So if we do the bullet after collision, all right, so we're looking at it after the collision. I'm going to finish this up in the last video, but we're going to look at the energy transfer after the collision for this scenario.